Okay, let's look at a pair of problems from chapter 27, one of which, number 16, is a 3-dot problem but probably shouldn't be, and the other of which, number 26, is a 2-dot problem and also probably shouldn't be. As I now realize it's useful to have the problems open in front of me and not just a drawing of the rough sketch of this. So 16 is talking about, to the best of my recollection as I struggle to flip to the right page, a solar panel. And when the solar panel is hooked up to an external resistor, right? Oh, I'm looking at chapter 27. Well, I'm talking about chapter 27. I'm looking at chapter 26 and being really confused as to why nothing is there, right? So a solar cell has a potential difference when it's loaded with a 500 ohm resistor, different one when it's loaded with a 1000 ohm resistor. So basically, this is our solar panel chilling out here. What we need to be careful with, and the distinction that this chapter is so keen on making, is that this is the EMF, the thing that is actually producing a voltage, which means that we have chilling out inside this little insidious internal resistance. And that is really what this is trying to hammer home, is this idea that there is an internal resistance in any battery of any sort, and depending on the load, that's going to alter the way your circuit behaves. Generally speaking, for this one, you want to start just as you would with any circuit, write down your loop rule. It's just a loop circuit. And you're going to have to do a little bit of algebra between the two different setups. But it is, aside from that, relatively straightforward. Could have sworn there were dashes there at some point. So, with that done, let's turn our attention to 26, which is significantly worse, despite being a 2-dot problem. So 26 looks like this. We have a battery connected across a uniform resistor R0, and there's a sliding contact that can move from this 0 centimeter point of contact to this 10 centimeter point of contact. So basically, we're making a circuit that looks something like this. We have 3 resistors, and we're conveniently ignoring the whole EMF thing again. So you still have this resistor R, and then depending on kind of what X you have put your contact at, this resistor here is X R0 over L. It's X over L of this R0 resistor. And this one is going to be L minus X R0 over L. So that if I add up these two resistors here, I'm going to get just R0. And you can check that for yourself. Now, ultimately, what they want you to do is to find the rate at which energy is dissipated, and that always means power, in resistor R, so in this one, as a function of X. So basically, if you want power, read the prints or something, but in this context, we know that's going to look like V squared over R maybe. Well, we don't know what the voltage across R is. That's also going to be a function of X. So what if instead, and probably a messy one, what if instead we went for RI squared? Wow, that's messy. Either of these will work. You can take your pick. But basically what needs to happen, you need to get either I or V as a function of X. Writing is clearly not my forte today. Function. And that is going to be pretty tricky. But the avenue you're going to want to take, more or less, is that you want the total resistance as a function of X. And so you can choose to either write that down by trying to get R, like R equivalent, which can work a little messy, or you can write this down as a series of loops. And there are many you can take. I mean, it's a single branch circuit, and try to solve that down, and find the current. Maybe would be probably your best bet. Either way, it winds up being a bit of an algebraic slog. So just prepare yourself, and if you take it step by step and just try to clean it up every time before you make any other substitutions, it should work out all right in the end. Good luck.